Hello everyone, let us look at integration of rational functions by partial fractions. Consider a rational function. A rational function given in this form, say f of x equal to p of x. This is a polynomial, p of x over another polynomial, call it g of x. When now we look at the degree, and then we find that the degree of p of x is m, and the degree of g of x is n. So if m is less than n, we say that f of x is a proper fraction. And as such, it may be expressed as a sum of partial fractions. We illustrate this using an example. Then it may also happen that m is greater or equal to n. So if m is greater or equal to n, then f of x is an improper. It's just like a fraction where you find the numerator is the bigger number compared to the numerator, then we speak of an improper fraction. So similarly, if the degree of the numerator is greater, or sometimes it will be equal to the degree of the denominator, then we speak of an improper fraction. And then before we decompose this into partial fractions, we may use what we call long division to get, you remember we have f of x equal to p of x over g of x, and then we want, say, to get a quotient. Let us call it q of x plus the remainder, let us call it r of x, divided by the divisor, which is still g of x. And of course, we are saying that this is the remainder, this is the divisor, divisor, and this is the quotient. This is the quotient, this is the divisor, this is the remainder. So Euclidean algorithm for polynomials, we understand that we can write this rational function in this manner. And if we manage to do this, then we will be able to decompose r of x over g of x into partial fractions. And then it will be easy to integrate the expression which will be under consideration. And then maybe before we do the integration, we must know the factors of g of x. In other words, we must first factorize g of x as far as possible. So you will find that when we are trying to factorize g of x, 4 cases are going to arise. Number one, it will be easy to find the linear factors of g of x, and in other words, g of x will be expressed as a product of distinct linear factors, then we'll be happy. It is easy to work with that one. Secondly, we may find that when we factorize g of x, we get factors which are repeating. So we get, yes, factors which are repeating. So the factors are not distinct. And in that case, we call that case number 2. And thirdly, you may find that when we factorize g of x, we end up part of the factors are irreducible quadratic factors. Then that is case number 3. And case number 4 is a situation where part of g of x is repeated irreducible quadratic factors. So we will look at all of these factors. I hope time will allow us to do so. Now let us quickly look at an example which involves case number 1. Case 1 is a situation where g of x is a product of distinct linear factors. So say, for instance, if g of x can be factorized into a1x plus b1 times a2x plus b2 times and so on until akx plus bk. If this is the case, then this rational function r of x over g of x can be written now as a constant, which we are going to find over a1x plus b1 plus another constant a2 a2x plus b2 plus and so on until the last one, let us call it ak over akx plus bk for that matter. Let us take an example to illustrate what we are talking about. In this example, we are to evaluate the integral of 2x cubed minus 4x squared minus x minus 3 divided by x squared minus 2x minus 3 dx, like that. So the first thing that we check is whether we have a proper or an improper fraction. So you can see the degree of the numerator here is 3. The degree of the denominator is 2. So 3 is greater than 2. Therefore, this is an improper fraction. And as such, we may, let me write here, we note that the integrand is an improper fraction. So what do? We use, or we may use, let me say we may, because some people say we don't want to use long division. We may use long division. So if you have another way, then it's okay, but we may use long division. And then when we use long division, what are we talking about? We just want to divide this. We have got 2x cubed minus 4x squared minus x minus 3. We divide this by x squared minus 2x minus 3. So when we divide, we are dividing 2x cubed by x squared. We get 2x multiply. Then we get 2x cubed. 2x times minus 2x is minus 4x squared. 2x times minus 3 is minus 6x. Then we subtract. 2x cubed minus 2x cubed is 0. 4x squared minus 4x squared minus 4x squared is 0. And minus x minus 6x is 5x. Minus 3 minus 0 is still minus 3. So it tells us that, okay, our fraction, maybe I should rewrite it here, 2x cubed minus 4x squared minus x minus 3 over x squared minus 2x minus 3, which is an improper fraction, can be written as the quotient. This is our quotient. This is our quotient. This is our remainder. This is our divisor, like that. So it's quotient, which is 2x, plus the remainder, which is 5x minus 3, divided by the divisor. The divisor, which is x squared minus 2x minus 3. Now, after doing this, we must be able to factorize that, which is easy for us, I think, which is easy for us to do. So now, if we factorize, let us concentrate on this part only. Now, 5x minus 3 over x squared minus 2x minus 3 can be written as x plus 1 times x minus 3. Because when you multiply the middle term, we have minus positive x minus 3x, which will give us minus 2x, and then the rest is fine. So we write this, we factorize that. It is like this, and then it will be equal to, and we recall that yeah, it is. We recall that now if we have it like this, we may have a constant. Let us just call it simple a over x plus 1 plus another constant because over that, which will be b over x minus 3. Now maybe I should explain something. You may note the way I wrote this factors here. I started with x plus 1, then x minus 3. Then some people may ask, what if we start with x minus 3 and followed by x plus 1? It's still okay, but the reason why we start with the positive, then the negative, is that on the number line, negative numbers are on the left of, are found on the left of 0, and positive numbers are found on the right hand side. All right, so if you equate this to 0, this will give you negative 1, this will give you positive 3. So usually we start with positive numbers followed by negative numbers when we're factorizing, based on that reasoning that if, say for instance, when we equate this to 0, we solve for that, and equate this to 0, solve for that, then we get that. Not saying that we are going to divide by 0. Division by 0, we know it's impossible. We don't divide by 0. So it's just a way of expressing it, but it doesn't really matter. So after doing that, let me bring that back here so that you can see. So after doing this, we multiply throughout by the denominator. If we do that, you will see that on the left hand side we have 5x minus 3. This is equal to a. We are multiplying by this. This will cancel out. Then a into x minus 3 plus b into x plus 1, like that. So this is going to lead us to situation where now we must find our A, we must also find our B. So there are several ways of doing it. I will show you the simpler one. To find A and B, now we use elimination. Let me say we may use what we call elimination, or yeah, something like that. So how do we do that? You just say, if you come here, you let x plus 1 to be equal to 0, then x will be equal to minus 1. So you let x to be minus 1. So you let x to be equal to minus 1, knowing very well that when x is minus 1, this will be 0. Okay, this will be 0. X is minus 1, you put minus 1 here, you get minus 4. You put minus 1 here, you get minus 8. So we get minus 8 equal to minus 4a. And then when we solve for a, we get a equal to 2. Then similarly, you can let your x to be equal to 3. If you let x be equal to 3, this will be 0. 3 here, this will be 15 minus 3 is 12. Equal to, you have a 3 here, 3 plus 1, it's a 4. This implies that B is a 3. There we are. So that's what we are interested in, 5x minus 3 over x plus 1 times x minus 3. It's equal to A, which is 2 over x plus 1, plus B, which is 3 over x minus 3, like that. Therefore, the integral of 2x cubed minus 4x squared minus x minus 3 over x squared minus 2x minus 3 dx is equal to, remember that after the long division, we got this integrand to be 2x plus 5x minus 3 over x squared minus 2x minus 3. So if we remember that, it means now we will have the integral of 2x. See, you have 2x plus, it's like the integral of 2x dx plus the integral now of a, which is 2 over x plus 1 dx, plus the integral of b, which is 3 over x minus 3 dx, like that. And this is equal to the integral of 2x is simply x squared, plus the integral of this one is 2 the ln of x plus 1, plus the integral of that one is 3 the ln of x minus 3 plus c, like that. All right, now that we have done example number 1, we may go on and look at case number 2. Case number 2. Case number 2. Case number 2. We find that now our g of x is a product of repeated linear factors. It may happen that, you find g of x equal to a certain factor multiplied by other factors which are repeating themselves. So say, for instance, a1x plus b1 times a1x plus b2 square that times and so on until a1x plus b1, this is 1, it's repeating itself until the k whatever. So let us illustrate this using an example. You can check on page 63, I think, yeah, page 63 of your notes. You find more explanations. Then the case here is you take your r of x over g of x, and you write a1 over a1x plus b1 plus, then you take your a2 a1x plus b1, you square that, plus until the last one, a k over a1x plus b1, then you raise this to the power of k, like that. Again, let us illustrate this using an example. If we take an example, they say evaluate. Then they gave us the integral of x to the power of 4 minus 2x squared plus 4x plus 1 divided by x cubed minus x squared minus x plus 1 dx, like that. Then again, the first thing that we do, let me write here again, we check the degree. You can see the degree of the numerator is 4, the degree of the denominator is 3. So again, we note that the integrand is an improper fraction. As such, we may use long division. We may use long division. So when we are using our long division, what do we have? We have x to the power of 4 minus 2x squared plus 4x plus 1. This is being divided by x cubed minus x squared minus x plus 1, like that. Then do it the very same way, divide this by that. It is x. Then multiplication, x times x cubed is x to the power of 4. X times x squared, we get minus x to the power of 3. And then minus x squared plus x, like that. Then we subtract, this will be 0. Above this one we have a 0, so it will be x cubed, because we don't have x cubed there, or it's simply 0x cubed minus x cubed minus x cubed for that matter. Then we get x cubed, like that. And then this one goes with that. You've got minus 2x squared minus x squared, which will give us minus x squared, like that. Then 4x minus x will give us positive 3x, and then there is nothing below 1, so we get a 1, like that. And then we do our division again. X cubed divided by x cubed is positive 1. We multiply, we get x cubed there. We get minus x squared. We get minus x. We get plus 1. Then we subtract. This is 0. This is 0. This is 4x. This is 0. So we can see now that what we started off with, x to the power of 4 minus 2x squared plus 4x plus 1 divided by x cubed minus x squared minus x plus 1 can be written in terms of the quotient, which is x plus 1, plus the remainder, which is 4x, over the divisor, which is x cubed minus x squared minus x plus 1, like that. All right. So the other thing that needs to be done is to factorize. Let me write here. Now, let us factorize the denominator. We call it g of x. Our denominator, we remember, is x cubed minus x squared minus x plus 1. There are many ways of killing a cat. There are many ways of factorizing this. One way is to note that you may group the terms. You have x cubed minus x squared, group them like this, minus x minus 1, group them like that. All right. So in this one, x squared is common, take it out. You are left with x minus 1 minus x minus 1. Then you note that x minus 1 is common, take it out, get x minus 1 into x squared minus 1. You realize that this is a difference of two squares. Factorize it. You get x minus 1 into x minus 1 into x plus 1, which I may write as x plus 1 into x minus 1 squared, like that. So we have factorized our denominator. We factorized our denominator, and if we succeed, because we have succeeded in doing that, now it means this part can be rewritten as 4x over x plus 1 x minus 1 all squared. Now you can see that this is a repeated linear factor. So we end up with a over the first one, which is x plus 1, plus b over x minus 1, plus c over x minus 1 all squared. That's how we do it. So we have got a over ax minus b1, which is the same thing as a over x plus 1. And then this, because now it's repeating, you have this, you have that, you have that. You can see this is the one that is repeating, right? So the one that is repeating is starting here, like that. This is different from that one. So we have it that way. After doing this, then we must find a, b, and c. How do we do that? We first multiply throughout by the denominator to get 4x equal to a into x minus 1 all squared, plus b multiplied by this, you will be left with x plus 1 times x minus 1. And then you get your c plus c multiplied by x plus 1, because this will cancel out. All right. Now when we get there, we must find our a, b, and c. How do we find a, b, and c? We may use elimination first. So we can let, using eliminating, we can let x to be equal to, say, 1. X equal to 1. X equal to 1. So if x is equal to 1, we understand that this will be 0. This will be 0. So we have 1 plus 1, which is 2c. to c it's equal to 4, like that. This implies that c is equal to 2. All right. And then secondly, we may let x to be equal to minus 1. And if we let x to be equal to minus 1, it means on the left-hand side we'll get minus 4 here. And then this will be 0, this will be 0, minus 1 here, minus 1 is minus 2 squared is 4. So this is equal to 4a, like that, which implies that a is equal to minus 1. Then we are left with b, and then we cannot eliminate anymore. So to find b, we may compare the coefficients. You don't have to multiply this out. You just look at it. By inspection, it's still fine. You compare the coefficients. Say for argument's sake, we choose to check what is the coefficient of x squared. You will recall that if you have an equation like this, and we are saying the left-hand side is equal to the right-hand side, so the corresponding coefficients of each term will be equal. So the coefficient of x squared on the left-hand side must be equal to the coefficient of x squared on the right. The coefficient of x on the left must be equal to the coefficient of x on the right, and so on and so on. Constants must also be equal. So we have chosen x squared. Then we look at the left-hand side. What is the coefficient of x squared on the left-hand side? We realize that we are starting with 4x, which means the coefficient of x squared on the left-hand side is 0. So we write our 0. Then we go to the right-hand side. On the right-hand side, we just check. When we expand this, we don't have to expand it, but we understand that when we multiply this, it will produce x squared. So we have ax squared. So one of the coefficients of x squared is a. Then when we come to this one, we can see x times x is x squared. So one of the coefficients is b, like that. So it means a plus b is equal to 0. And then this implies that since a is equal to minus 1, it means b will be equal to 1. And we are done. Therefore, what we are interested in is the integral of x to the power of 4 minus 2x squared plus 4x plus 1. Divide this by x cubed minus x squared minus x plus 1 dx. This is equal to x plus 1, and then what we just decomposed into partial fractions. So we have our x plus 1, which was our quotient, and then our a is minus 1, so we will have minus 1 over x plus 1 there. And then our b is 1, so we have plus our b is 1 x minus 1. And then our c is 2, so we have plus 2 over x minus 1 all squared. Remember, what are we doing? We are integrating with respect to x. We are integrating with respect to x. We are integrating with respect to x, like that. So if we do that, then we can quickly see that the integral can quickly see that the integral of x plus 1, the integral of x plus 1, let me write it here. The integral of x plus 1 is equal to x squared over 2 plus x. And then the integral of 1 over x plus 1 is the ln of x plus 1. Integral of 1 over x minus 1 is the ln of x minus 1. The integral of x minus 1 all squared will be minus 2 over x minus 1 plus c. You may check that one. So we have now looked at case number 2 of our rational functions. Let us quickly go to case number 3. Case 3. Case 3 is where g of x contains distinct, irreducible, quadratic factors. So we illustrate this using an example. You can check on page 63. We illustrate the decomposition using an example. So let us take as an example situation where they say evaluate the integral of 2x squared minus x plus 4 divided by x cubed plus 4x dx, like that. Now, as a solution, we note that 2x, okay, the first thing, of course, is to check whether this is a proper fraction or an improper fraction. The degree is smaller than that one. We are happy. We don't have to use our long division. So 2x squared minus x plus 4 divided by x cubed plus 4x can be written as 2x squared minus x plus 4 over, we factorize our denominator. We realize that if we take x, which is common out, we are left with x squared plus 4. And we cannot factorize this any further using real numbers. We cannot factorize that further using real numbers. Thus, 2x squared minus x plus 4 over x into x squared plus 4 can be written now as a over x plus, now this is a quadratic, so we write bx plus c over x squared plus 4 for quadratic. Bx plus c. So this will be a linear like that. This is a constant. This is just a linear something with degree 1. Then like that with 2 constants appearing this way. All right. So after that, we multiply throughout by the denominator. Then on the left-hand side, we'll be left with 2x squared minus x plus 4. This will be equal to our a into x squared plus 4 plus our bx plus c multiplied by x, like that. And then we find the constants a, b, and c. We may first start off by using elimination, and then elimination will let x to be 0, If you let x to be 0, this will be 0, this will be a 4, this will be a 4. So we okay, let us see how far we can go. This will be 0, so it will be a 4 here. And this side, this is 0, this is 0, this is 4a, which implies that a equal to 1 for that matter. And then from there, we want to find b and c, and then we realize that we can no longer use elimination here, so we compare the coefficients. Maybe I should put it like that. I will show it to you again. Compare the coefficients. When we compare the coefficients, what we are doing is we can start off by looking at the coefficients of x squared. And then on the left-hand side, we can see we have got a 2 equal to, now we check on the right-hand side, you can see when we remove the brackets, we'll have a, which is a coefficient of x squared, and then b, so a plus b. So we have a plus b, it's equal to a 2. Now, if we are saying a plus b, it's equal to a 2, and a, it's 1, it means b a plus b, I mean, because a it's 1, it means b it's equal to 1 also, like that. And then furthermore, we can move on to compare the coefficients, say, of x. On the left-hand side here, the coefficient of x, it's -1. On the right-hand side, this will not have any x, but this one will have a c, cx. This one will not, it will be a square, so c. So we have on the left, it's -1, as we have noted. On the right-hand side,